Hello. Kimse var mı Eleko'dan? Yok herhalde. Samil. So just 2 minutes left for our session. So it looks like we are just missing one author for the paper, I think 37. Oh, I think more than one author. Because Ali, Osman and Serra are for the same paper. So we have just the authors of 2 papers. So if there are any authors from the attendees, please raise your hand so that we can put you in the panelists. So just to remind you that the session is like 1 hour and a half. So this will be like 15 minutes presentation, 5 minutes question and answer. So please arrange your presentation accordingly. So if it's okay with the ELIP organizers, it's like 10:30. So we can start with the first paper. It's going to be presented by Mehmet Samil Soyar.
Hello, Professor.
Okay, great. So I think you can go ahead.
Yeah, should I open my camera and share my screen?
I mean, I guess you have to share your screen. Yeah, opening the cam is up to you. I mean.
Okay, I will open my cam. Thank you. Can you see me? So first of all, I would like to apologize because of my voice. I feel a bit sick. That's why my sound will sound a bit different. I will start with my presentation. Our paper was about a deep learning-based plant disease detection application. The authors that contributed in this article are Elmas, Ismail, Mervan, Özcan, Master of Science Fatih and Tuba Conka Yildiz, our advisor professor from our university. I worked in this project, in this study, while I was working part-time at Siemens, and I was a student in Turkish-German University. The agenda of this presentation will start with the introduction, and then comes the related literature, then comes methodology and outputs of the systems, and we will finish it with conclusion and question and answer. So I will start with my introduction. Our motivation for this study was the effects of the diseases on leaves on farm industry and food industry. As you can see, when people want to plant and get economic benefit from the leaves and also vegetables, there are massive losses when there's a plant disease in the farming area. That's why if you detect it, if you find it before it's separated to other plants, it will be really better for the people to gain benefits. We wanted to minimize the crop loss and to understand the cause of the symptoms, whether it is biotic or abiotic. Motivation for using machine learning is that for this type of content, there are many studies on the laboratory with convolutional neural networks, but uh, most of them are not efficient or neither practical to use. Some of them are used for weed detection, classification of crop pests, and identification of plant disease. Then I will continue with related literature. So, first of all, I will talk about digital image processing and deep learning. The terms of deep learning or neural network refer to multi-layer artifactual neural functions. These structures have been recognized as one of the most powerful tools in many fields in scientific literature in recent years and have become very popular because they can process large amounts of data. One of the most popular deep neural network is convolutional neural network. It is an AI tool to analyze and process visual data. That's why we have used convolutional neural network in this project. Convolutional neural network gets its name from a mathematical linear operation between matrices called convolution matrices. Also, we have used digital image processing to augment our data and make it more efficient to use. Uh, then comes TensorFlow and Keras. As you can see, we have made an architecture. This architecture has been created with 4 layers, and we have used in these layers max pooling 2D, ReLU activation, batch normalization. These are conv2D layers. What is a conv2D layer? Is a 2D convolutional layer. This layer creates a convolution kernel that is convolved with layer input to produce a tensor of outputs. In these conv2D layers, we have used max pooling 2D layer and then a ReLU activation layer. At last, for the flatten, we have used softmax activation because of the class counts. We have 38 different classes. That's why we have used softmax activation. Softmax converts a vector of values to probability distribution. Softmax returns a tensor which all values are non-negative and gives a sum to none, 1. For the architectural production, we have used TensorFlow and Keras. These are open source libraries on Python to use in machine learning systems, especially on convolutional neural networks or computer vision. Then comes plant pathology. Here you can see some leaf disease examples. We have seen that when we have made our research, we have seen that there are 2 types of diseases, one biotic and one abiotic. Biotic caused by living beings like bacteria and viral causes. Abiotic caused by inanimate ecological conditions, soil competition, wind, or soil salinity. Now I will talk about our methodology. This is a conceptual structure of the system. In this figure, you can see that the photo of the leaf is first taken from the user to the phone gallery or by taking it with the camera. This photo is then sent to the server created for the application via the internet server to determine the state of the plant. It is processed and analyzed through the model the trained model, and that model will be created in CNN. Then the output of this process can be sent to the Android application back with the same internet server. and we can give the output that if the leaf has a disease and what the disease is. And this is a conceptual structure. Then I will talk about the system structure. So first of all, we have made a data set and we loaded it with Python and TensorFlow. Then we have created a CNN algorithm, a deep learning algorithm, a CNN architecture to use in our system. Then we have created an internet server with Flask, a library of Python, and we have created a GUI with Android Studio, which was coded in Java. And then we have implemented all of them integration. We have integrated all of them, and we have used get post commands of Flask to give the photo and get the output from the server. The server was created in our local domain, and it could be further developed by using an cloud system like Amazon Web Services. And we have made an Android application. This and Android application is just for the the basic system, and it has been designed and presented in a simple way to make that anyone can understand what is going on. So when we open our app, you can select open camera or open gallery, and you can take a photo or choose a photo from your gallery. And then when you click examine the leaf, we post the leaf to the localhost, and it classifies the disease and give the disease back. So for the outputs of the system, the first one is dataset. We have 87,867 images that we have used in this trained model to train the system. 80% of the images have been used for the training purposes, and 20% was used to validate the output of the trained model. There are 38 different classes on this project. For the system performance results, as you can see in the graphics, we have created a model that has 98.88% accuracy, and the loss is close to 0. So we have researched in Kaggle and the open source websites that in the same dataset, what happened with the other models. We have found that 2 different pre-trained models have been used for detecting life disease or classifying them. The accuracy of these systems were compared with our proposed model, and we have seen that the best result has been from our model. But the Inception V3 model had a bit lower loss, and the results are, as you can see in the table 2. As a conclusion for this project, we have made a CNN-based model to detect the common leaf disease. We have made an Android application and integration for the web services, and we have determined that the application can work with an accuracy of 98% for the detection of the leaves. And I would like to thank to my colleagues and thank Elako for reviewing my paper and giving certainly really good comments about my paper, and we want to develop ourselves with the comments that have been given. Thank you so much for listening, and I will take the questions and answers now.
Thank you, Mehmet, for the presentation. Your voice was pretty okay, so no worries about that.
Thank you so
let's
much.
ask the audience. Maybe we have some nasty questions for you. So any questions from the audience? Okay, so if not, I have a couple, obviously, since I'm the chair, so they are expecting me to ask questions.
Yes.
So I'm just curious about this separation of your data set. You
Yes.
said something like 80% was used for educational purposes. You mean training?
Training, yes. Training.
Okay. So have you done any testing in the
We have made, yes, we have made some testing, but we have made it with outside of our data set, not in our data set. For the
So how were the results for the testing? Because the generalization capability of any DNN is basically evaluated with respect to the testing. So training and validation losses are pretty nice, but we always want to see how it's good in the generalization, so the testing performances. So was it still high, like 98%, something like this, or lower?
Yes, you're right. That's not really realistic when you say it like that. The accuracy will not be with the testing results, will not be the same as testing results. We haven't got much time for the testing, and for future work, we have to make a testing process. Thank you for your question.
But you have this kind of huge amount of data, and you use all of the data, like 80% for training, 20% for validation. Yes. So humble advice, next time use 70% for training and validation, 30% for testing. So you have huge amount of data.
Yes.
So you could easily done this in this manner. My second question is, like, if I'm not wrong, you have compared it with the ResNet Inception version 2, I think. Yes. And the image size over there is like 300 to 300 pixels, but you have a smaller image size, right? In the paper, it's like 64 by 64.
Yes.
So was there any main purpose to reduce the image size to 64 to 64? Because with the smartphones, we can get really high resolution photos.
We have thought about the performance on training. It was with the high amount of data, as you said, it was a bit hard for our local system, for my computer to train it. It took a lot of time. That's why I couldn't make it on the bigger resolution. But thank you for your consideration.
Okay. But the ResNet was not fine-tuned by you, right?
No, not from us. ResNet was used in a Kaggle project that we have found and cited in paper. Thank you for your advice.
No problem. So it looks like we are running up to time. So thank you, Mehmet, for your presentation again.
I thank you again.
The digital applause for you. So I think we can move to the second presenter, which should be from ITU. Ali, Osman, and I guess Serra are going to present simultaneously.
Professor.
I will start.
Okay, so humble advice, speak not simultaneously. Okay, the floor is yours.
Yes. Dear participants, welcome to our presentation. It's a great pleasure for me to present our study today. I would like to introduce our study, Agent-Based Route Planning with Deep Q-Learning. The authors are Professor Dr. Mehmet Soylemez, Ilhan Tunc, Ali Osman Koroglu, Ali Emre Edem, Ozge Elmas, and my name is Serra. As you can see, we will examine our study in 6 parts. We will look over quickly the first part, which is Introduction and Traffic Simulation Program. Then my study mate, Ali Osman, will present Q-Learning and Deep Q-Learning, System Overview, Simulation Results, and Conclusion parts. As already known, traffic congestion is a huge problem nowadays. The increasing individual mobility and population lead to traffic congestion, especially in metropolises. Also, multidimensional network topologies in metropolises such as Istanbul can cause accident and indirectly traffic. If we consider that traffic congestion is a complex and unpredictable, then we realize how it becomes a serious urban management problem. Considering these issues, it can be said that the traffic decreases life quality in many aspects, such as wasting time, human psychology, noise pollution, and carbon footprint. According to European Union research, transportation is responsible for more than a quarter of total greenhouse gas emissions. It was determined that 73% of emission amount was caused by road transportation. The inspiration for this study comes from handling the solution of traffic control problems to decrease the amount of time spent on the roads, to make sure the roads are safe and comfortable, and to prevent environmental crisis. Traffic control techniques are developed, which are called intelligent transportation systems. We will discuss the feasibility of the route planning method between the intelligent transportation systems. As a simulation environment ensures easy modeling and saving time, SUMO offers detailed simulation possibility. We used SUMO environment in this study. It is open source and can be used on any operating system. Thanks to easy feasibility, the traffic scenarios were produced using SUMO's interfaces. SUMO allows the production of many types of vehicles to increase the reality of the simulation. Since route planning is worked on just taxi and passenger, it was used standard vehicle and passengers in the study. We didn't use another type of vehicles. In addition, the calculated of carbon dioxide emission values can be used to observe evaluation results. And traffic lights were also used as a parameter. Then Osman will continue. Thank you.
Thank you, Serra. Hello, everyone. I'm Ali Osman. I'll continue the rest of the presentation. I would like to mention the Q-learning method we used in our study. For complex systems such as traffic flow, the Q-learning method is a suitable method. Here we can see general schema of the Q-learning process. The main purpose of the Q-learning process is to select the best action according to the Q value by an agent in the environment, and this action affects the environment. This effects on the environment is obtained by agent as states and reverse values. And then with these values, the Q table is updated, and this process is repeated over and over iteratively to achieve optimum Q table. And one of the tricky points of Q learning is biasing with limited experience. All values of Q table are initially 0. If there is no exploration right of agent, it will be inclined to select the actions in first iteration, even if these actions have small values, because unexplored actions have 0 Q value. Here, epsilon is a probabilistic value between 0 and 1. Epsilon per each one action will be random. In our study, epsilon is selected adaptive as 1 per 1 probability for first iteration and 0 per 1 probability for last iteration, and it decreases linearly between first and last iteration. Even if Q-learning method is suitable for complex systems, it has some disadvantage. The Q table has huge memory cost for large state and action combinations. A neural network trained with a limited number of states and Q values may be sufficient to represent the Q table without huge memory codes. This method is called deep Q learning, and we use this method in this study. Now I will introduce the system that we want to control. Our system is a traffic network with active traffic flow. In network, there are 12 interconnected rows. All rows in the system have 2 lanes. There are 5 intersections with traffic lights. The length of each road is 450 meters. And there is a taxi agent to complete missions. The agent's task is to pick up the passenger waiting at any point in the road network and drop them off at the passenger's destination point to complete it for all waiting passengers. And here we can see the traffic network. Here, in the direction of the arrows, an asymmetrical traffic flow was created. Standard type of vehicles were generated at random times in symbol. And this asymmetry and randomness have been chosen to approximate real chaotic traffic flow. And here you can see the specifications of neural network model that was used in this study. The artificial neural network consists of 4 layers, and each layer contains 400 neurons. To accelerate learning, batch learning method was used, and batch size is 100. Number of epochs is 800, and learning rate is 0.01. The neural network in this image is not exactly the same as the real model. It's a scaled down version. Finally, in learning model, rule function is used as activation function for neurons. Now I will talk about some details of the deep Q learning process of text agent. Firstly, the size of action set is 3, but agent is not free to select all action each intersection. It's allowed to taxi 3 different options for 4-way intersections, but at 3-way intersections, tax agent can select only 2 different actions. And another important component of the deep Q learning is a reward function. In fact, we use this function as a penalty expression based on the ratio of the past simulation time to maximum simulation time and multiplied by passengers waiting for a taxi. And here, the time spent on the current road. And this expression gives current reward. After each decision process, current reward is added cumulative reward. And another important part of the deep Q learning is the states. In the study, our comparison criterion is the contents of state vectors. And for this purpose, 2 state vectors are created and obtained effects on learning process. The first state vector consists of position information of taxi agent on 2-dimensional plane and position information of 3 neighbor intersections on 2 dimension and position of target point on 2 dimension and vehicle density of neighbor roads. Total, this state vector contains 13 state elements. And in addition to vector 1, vector 2 contains information about traffic light status of neighboring intersections, and second vector contains 19 state elements. We can clearly see the state vectors here, and here we can see an example case of how to collect position informations from environment. In this case, position of taxi 0 for X position and 50 for Y position. Also, positions of neighbor intersections can be seen. In fact, this information gives the agent an idea of what position the taxi will reach as a result of the action it will take. In this example, the taxi appears on the pickup part of its mission because there is a passenger's waiting for taxi, and position of this person is the target position for now. And in this example, it's seen how traffic density information is obtained. The number of vehicles on the neighboring roads is transmitted to the agent. And this example, we can see what the traffic light information contains. Information of traffic light colors and remaining time are transmitted to the taxi agent. With these states, we aim for the agent to choose an appropriate action taking into account the traffic lights. And here we can see an example scenario. A taxi at any point must first arrive at the pickup point where the waiting passenger is. After the taxi picks up the passenger, we point the point where the passenger wants to go will be new destination position. To drop the passenger off, the taxi must reach the destination point. This process lasts until all passengers reach their desired destination and the mission is over. And here we can see the change in the average waiting times of the passengers in each iteration. For both of two-state vector, average waiting times decreases, but in learning process, some differences can be noticed. It can be seen that when traffic light informations are not used in the state vector, process of reaching optimum value is more oscillating. And also here we can see that the agent is successful to issue optimum reward value into situation, but issuing optimum value without traffic light information is harder than issuing with traffic light informations. And as a conclusion, we can say that in road selection, traffic route information and position information are important criteria and have a direct impact on the completion of the tasks. When this state information is used as input for the deep learning model, it allows the agent to find the appropriate action values after sufficient training. In addition to position and road information, meaningful site information such as traffic lights can be beneficial to the learning process. And in the near future, for a real traffic scenario, route planning optimization can be achieved by training autonomous traffic agents with deep Q learning method. And I would like to thank for your attention. I can try to answer if there is any question.
Thank you, Ali and Serra, for the presentation. So let's look if there are any questions from the attendees. If not, as usual, I have to ask you a couple of questions. So it looks like silence again. So, I have just, so let's say two, maybe at most. So the motivation is pretty nice regarding the pollution and so on. But if you look at your reward function, there is nothing related to pollution. So try to consider these kinds of components in your reward. Now it looks like you want to create this kind of crazy taxi driver that picks up passengers as much as possible, as soon as possible. Regarding the traffic rules and so on, how feasible is to employ this, for instance, agent in a real world environment?
Yeah, actually, we want to control a fleet of taxi, but duration of the study, we had to limit our study because of the hardware limitations and time limitations. And the results are these for now.
So how many times have you repeated the training? So it looks like you just provided the results for a single seat. So if I would repeat the experiment like 20 times, would I end up still again with the almost results or not? Because there is lots of randomness, stochasticness, and
yes,
environment in learning these kinds of, because you are using this vanilla deep Q learning structure eventually.
Yeah, Really?
So what I suggest you is to repeat this experiment at least 5 times, present average, minimum, maximum, standard deviation results. And then I think what we see, like to see this kind of simulation where you employ the policy in the simulation environment. If I would create a random simulation environment and employ your agent, we're able to move from point A to point B successfully without crashing and so on. So it looks like we have a question. So Mehmet, Samil is asking, I would like to ask that, is there a similar usage of this system on Google Maps or Yandex? This is like a future work question, I guess. So any comments, Serra or Ali Osman? So do you think we can integrate this stuff to Google Maps or Yandex?
Actually, I guess there's some usage on the route planning only, but we want to control the traffic agents also.
Right. It looks like it's possible, but the problem description is different here. So Mehmet, if you have further questions, because we are running out of time now, you can directly email Serra, Ali, or the other authors, I would say. So I think we should move to the next presentation. So Serra and Ali Osman, thank you again for the nice presentation.
Yeah,
Thank you.
thank you.
So let's move to the next one. I think the next one will be presented by Funda, and she's around.
Okay.
Oh, hey, Funda, the stage is yours.
Yes. Wait a minute. Okay. Welcome to my presentation. Is everybody can see my screen?
Can you make it full screen, Funda?
Yes, I'm trying to do it. Okay. Is it normal?
It looks like you are using a second screen, I think, and you are sharing the wrong screen, or?
No, actually.
Okay. So just try to make the presentation a bit larger, because still it's not in the presentation format right now.
Okay. Wait a minute. Sorry for being late. I think there's a problem. So
So it looks like Eleco is saying, okay, so people are writing me something, but I have no idea what to do. So you unshare your screen and then share it again.
okay.
Okay, so
Stop share.
okay, so now give it another try. Okay.
Okay, can you see now?
Yeah. Go ahead.
Okay. Okay, welcome to my presentation. I'm so grateful to be part of this conference. I'm continuing my PhD studies with my advisor, Professor Dr. Serdar in Electronics Engineering Department at Istanbul Technical University. I am working as an instructor at Altınbaş University's Electrical and Electronics Engineering Department also. In this presentation, I will give a general information about power amplifiers. As a second step, I will talk about the model we propose in this study. In the last step, I will talk about our results. Okay, power amplifier is one of the most important parts in any wireless communication system, but unfortunately, it suffers from some problems that need to be considered very carefully to increase its efficiency. The nonlinearity behavior is one of the major drawbacks of the PA that appears when the PA operates in near its saturation region actually. The nonlinearity problem causes unwanted signal properties such as gain compression, intermodulation distortion, phase distortion, spectral regrowth in adjacent channels. And to solve this nonlinearity problem, digital predistorters are used commonly to build the digital predistorter. Most DPD works use memory polynomial method. Although their performance is acceptable, there is a huge complexity about the computational. So in some cases, there's hundreds of coefficients. So to get rid of this complexity problem, we proposed a deep neural network method for this methodology, for this studies. And to train the predistorter, the majority of the DPD works use an indirect learning architecture actually. In an indirect learning architecture, an inverse model is learned using a post distorter, which is then copied to the predistorter. In figure one, a plot of amplifier output versus input power for a single frequency is seen. The amplifier has a linear region of operation where gain is constant and independent of the power level. The gain in this region is commonly referred to as small signal gain. As the input power increases, the amplifier gain appears to decreases, and amplifier goes into compression actually. This is 1 dB compression point, which is defined as the input power also. In this position, the gain is decreasing actually 1 dB. So if the input is sinusoidal, in this situation, output of the amplifier won't be actually sinusoidal because of the compression point. Some of the amplifier outputs appears harmonics and some signal distortions on this point, and also on saturated point, input change won't be seen at output actually. In this example, which is on right side, which is on right side, actually this is the amplifier results. Input is increased 3 times. So for input 1, the output is 3 actually. For input 5, for input 2, output is 5. For input 3, output is 6 actually, and between 5 and 6, there is 1 dB decreasing. So this is the 1 dB compression point for this example. Now I will talk about the proposed model in this study. We choose to use deep neural network to model PA and DPD separately. Deep neural network training is performed to model PA at first. PA block using PA input and output data that we measure in other software. And DPD block is modeled using deep neural network by taking inverse of PA model coefficients actually. In comparison to the polynomial-based technique used, deep neural network-based predistorter has the benefit of being more versatile actually. The DPD designer would frequently hit hundreds of coefficients for large systems before pruning any that have no effect. And deep neural network situation will solve the complexity problem for huge coefficient situations. In this model, the following are the key contributions of this work. A novel PA algorithm based on deep neural network is proposed at first. PA model is created again by using deep neural network. As a second step, using PA input-output data, we create the DPD model. And as a third step, comparison of the performances of deep neural networks created with different layers. We propose 2 different deep neural networks actually, and we compare their results. And as a fourth step, the PA and DPD blocks are linked together in a cascade to get the total results. We separately create PA, and by using PA coefficients, we separately create deep neural network, and we cascade them to create all system. As a first step, deep neural network PA system overview, let's talk about it. In step 1, we use AVR microwave office program to create PA coefficients actually. We run AVR program and we get the PA input and output data as an amplitude and the phase. After that, we export the data to Excel and we use for deep neural network MATLAB environment. We use this Excel file in our MATLAB environment and we run DNN, deep neural network code to get the PA coefficients. NIV PA and the AVR PA. NIV PA, which is created by using deep neural network, and the AVR PA is compared, and the result is when we check its error value, the result is very similar. So this is a good way to create the power amplifier by using deep neural network actually. This is AVR model that we used. And here from the left side, we take the measurements, and from right side, from output port, we take measurements again to create amplitude AM characteristic actually. We use amplitude values for this. Input power and the output power values gathered from AVR program, and then we plot the graph to see AM to AM characteristic. By using amplitude and the phase values, we create our deep neural network model by using BLSTM layer, and the results are approximately the same. In next slides, we will see the tables for the error values. These are only graphs. And deep neural network system for DPD. Actually, we take the inverse of the PA for output changed to input and input change to output actually to create the DPD coefficients. After that, we get deep neural network coefficients for digital predistorter. And totally, the total system is created by cascading PA and DPD obtained by using deep neural network. At first, for AM coefficients, for power amplifier, we cascade these coefficients with digital predistorter coefficients that we create by using deep neural network again. As a second step, for phase, this is for amplitude actually. For phase, PA, AM, PM coefficients cascaded with the DPD coefficients. And totally, by using phase and the amplitude values, we get the linearized PA as a total system. We want the comparison of our results, the effects of LSTM and BLSTM. We repeat all steps for LSTM and BLSTM for deep neural network. And when we compare the results for same iteration value and for same activation function, only we changed LSTM and BLSTM layers. When we check the results, BLSTM layers give smaller error value. So to create total system, we prefer BLSTM layer actually. Difference between LSTM and BLSTM, both of them time series, but in LSTM, it starts to using data from start to end, but for BLSTM, it uses data for regression, start to end, and end to start at the same time. So there's two ways. Because of that, error value is decreasing actually, and it give us the better results, better values for our system. This is the AM characteristic with DPD and the without DPD. Actually, as you see, this is the 1 dB compression point. Without DPD, the saturation value is smaller than for with DPD results. So with DPD, after 0, actually, the output value is linearized, and it's more linear than the without DPD results. And actually here, with DPD, the phase distortion is decreasing. In first slides, we said that without DPD is sharper, actually sharper than the with DPD results for AM/PM distortion. For DPD power amplifier system, 2 separate simulations are completed for LSTM and BLSTM, for PA, for DPD separately, for 4 different simulations. And we get the total results by using these simulations. When the results are evaluated, it is seen that deep neural network structure created with BLSTM gives results with smaller error actually. For this reason, BLSTM layer is preferred to create the total system. 2 separate deep neural network structures are created for amplitude and phase for power amplifier, likewise for deep neural network block 2. And finally, linearized power amplifier is obtained by combining phase and amplitude values. The power amplifier achieved from DPD output values actually. If we summarize it, totally for PA, there is 2 different simulations. There's actually 4 different simulations. One of them is for LSTM, and the other one is for BLSTM. One of them is for AM/AM characteristic, and the other one is for AM/PM characteristic for phase degree. In DPD side, there's again 4 simulation performed. One of them is LSTM and the other one is BLSTM. One of them is for AM/AM characteristic and the other one is for AM/PM characteristic. And totally, we create the system by cascading at first DPD and PA. DPD is the beginning point of the system, and PA is connected after DPD to get the linearized output. Thank you for listening me. If there's a question, I may take the questions. I can't hear you because your voice is closed.
Okay, thank you. So,
sorry.
Still getting used to the Zoom meeting. So thank you for the presentation. So if there are any questions, now would be the perfect time. So silence as usual, I guess. Okay, so as usual, let me ask or try to understand the idea of the paper, because I mean, you are the expert about this power stuff. I have no idea about these kind of circuit stuff. So I'm just curious about the deep learning side. So when you said you extracted data from the simulation environment, but what's the size of the data? What's the volume of the data? So how big data are we talking about?
Okay, actually 100
sample points.
Yes, 100 sample points.
So do you think if you would just employ this kind of monomial polynomial approach, you would get like a similar result instead of using this kind of LSTM-based stuff? So have you tried this kind of fit polynomial approach?
Yes, it can be used memorial polynomial approach too. There's so many papers about this. But this is the new approach, and for the huge systems, actually, this is the small system, but there can be huge systems too. For huge systems, the deep neural network is the better way to get rid of the complexity of the calculation, actually.
So yes, you are right. So have you tried this kind of fitting a polynomial for your data set?
No, I haven't tried.
It's always nice to see this kind of basic approach comparisons so that we can see the real improvement of the deep neural network stuff usually.
Okay. Okay.
Have you done any training, testing, validation in training the deep neural network, or was everything used for training?
No, approximately 80% is used for training, and 20% is used for testing.
So how are these kind of accuracy performances, I mean, for training testing? I mean, do you have the graphs, so how the loss is changing and so on?
Yes, you are right. Beginning of the graph is a long time, it's linear. So if it's homogeneous, the result won't be seen like a comparison point. It seems as a linear directly. And I try to say from all points, from comparison point, from saturation point too. So I decrease the linear part coefficient numbers to get rid of this problem.
So what I would suggest you is like to check this kind of inverse neural network stuff. So I think it would perfectly fit to your application area. Thanks again, Funda, for the presentation, because we are again approaching to the next presentation time. So thank you, Funda.
You're welcome.
We are ready for the next one, which is, I think, will be presented by Hasan Nimci. Hasan is here.
Yes.
Okay.
Hello, everyone. Let me share. Yeah. By the way, can you hear me?
Yeah.
Okay. Okay. Let me share my screen. It should be on the screen, I guess.
Yeah.
Okay. Okay.
It is always nice to see the presenter. So if possible, open the cam, I would say.
Sure, of course.
Great. Okay, so stage is yours.
Okay. Hello, everyone. This is Hasan Kilimci. I am working as a senior engineer in Orion Innovation Turkey. Also a student in Kocaeli University Information Systems Engineering. I will talk about our paper that we have sent to conference about deep learning based decision integration strategy for the prediction of Istanbul Stock Exchange. Okay. My presentation will have steps about an overview, objective, methods, methodology, and experiment setup and results. As an overview, Istanbul Stock Exchange is described as BIST 100 index that's commonly employed abbreviation for the stock exchanges of Turkey. BIST 100 is a fundamental index of national market that is always followed by many analysts, traders, and is comprised both stocks of BIST 50 and BIST 30. Sorry, I have to get this phone. unknown numbers. Sorry about that.
Right.
Also, assessment of investments, analysis, and resources with the various parameters, conducting fundamental and technical analysis of them in BIST 100 is performed by many investors, analysts, and researchers. And it's very popular nowadays in Turkey. Also, in recent years, artificial neural networks and deep learning methods have become eye-catching topics in various research fields, mostly in pattern recognition, natural language processing, video image processing, and also for time series forecasting. We know deep learning methods exhibit better predictions than widely used machine learning approaches. Deep learning methodologies are primarily employed to ensure feature engineering automatically by training features with minimum external effort to provide that data is demonstrated in a substantial way with the help of deep neural networks. Objective of our paper is focusing on investigating daily price prediction of Istanbul Stock Exchange. The methods we used are multi-layer perceptron, MLP, convolutional neural networks, long short-term memory networks, and decision integration strategy. Multi-layer perceptron is widely used for supervised learning algorithm among other models of artificial neural networks, and mostly for estimation problems in the literature. It has input layer, hidden layer, and output layer, which are fundamental of multi-layer perceptron. And it can be composed of many layers with activation functions. Powerful computing sufficiency is provided by MLP because of facilitating the solution of non-linear problems. We also have, we will have also CNN convolutional neural networks. This is, as mentioned, was mostly used for image and speech recognition problems and natural language processing. It has layers, generally input, convolution, pooling, and fully connected layers. Long short-term memory networks. This is a variant of RNN, and it captures long-term dependencies and relations in the sequence data. It also holds the conceptual semantics of information and long-term dependencies between the data. Decision integration strategy. This is employed by the way of consolidating the strengths of various techniques into a single corroborated method, as each technique can be more sensitive and can have some disadvantages under various environments. Gathering decision of each model ensures more efficient and potential results at decision-making step. This is done by in our with the gradient boosting regressor at the decision integration step. Our proposed framework is to forecast the price of Istanbul Stock Exchange via deep learning-based decision consolidation approach. For this purpose, our data is collected using Selenium library from investing.com. We have 18 stock market movements, prices for 10-year period time. Also, in addition to those, 10-year US bond, 5-year US bond, dollar index, USD, Turkish lira rate, and Euro USD rate included for 1 February 2011 to 1 February 2021. Our proposed framework, in our framework, we have following stock market data, as I mentioned on the previous slide. We have stock market prices from Asia, Europe, and United States. We have Dow Jones, Nasdaq, S&P 500, Shanghai Stock Exchange, Korea Stock Exchange, National Stock Exchange of India, Tokyo Stock Exchange, Karachi Stock Exchange, Moscow, and Thailand. Also Frankfurt, Brussels, France, Amsterdam, London, and Madrid, and Italy. And our data set is composed of 3,655 instances, and including stock exchanges and other instruments, we have 23 features. Once we have the data set, we use MLP, CNNs, LSTMs, and decision integration strategy for our model. To avoid overfitting, we use L2 regularization and edit dropout layers. Our experiment results, we had comprehensive experiments and monitored the performance of each method to forecast the price of Istanbul Stock Exchange. Our data set is used as 70% for training and 30% for testing. And during this monitoring, we have used mean absolute percentage error, mean absolute error, and mean squared error to predict the performance of each technique. Our experiment results are, we have mean absolute percentage error values for MLP 6.99, for CNN 5.70, and for LSTM 6.66, and for decision integration strategy it's 4.93. For mean absolute error 0.16, 0.06, 0.07, and 0.04. And for mean squared error, it's 0.21, 0.0061, and 0.0077, and 0.0049 for our models. So according to our experiment results, the best performance was on decision integration strategy carried by a gradient boosting regression for these learning techniques. From the deep learning techniques, the best one was CNN with the mean absolute percentage error of 5.70. This is the training validation loss and mean absolute percentage error results of CNN model at 70% training set size. As we can see from this figure, it's getting stable after around 100 epochs, and it's parallel. And this is the forecast of BIST 100 index at training set size by decision integration strategy. It's the blue ones are actual and the yellows are predicted values. Tests are starting from 2018 around and ending up with the 2021. And thank you for listening me. If you have any questions, I may try to answer them.
Thank you, Asad, for the presentation. So let's see if there are any questions, comments from the audience.
Sure.
Looks like nothing as usual, right? So Hasan, I'm just curious about what's going to be the Turkish dollar rate next week, according to your model.
Yeah, let's say before.
So have you tried this kind of recent data, work your model in prediction mode?
I have done for Bitcoin, but not for BIST 100.
Right.
But I think instead of Bitcoin, I should be doing USD rates.
Yeah, I mean, it would be really nice for the audience to get an idea if you should buy US dollar next Monday or not.
Definitely, definitely, yeah.
Yeah. So regarding the loss function that you have presented, so what was the loss function? Was it like conventional root mean square error only?
Yes, yes. Only mean square error is used, but you know, we may try to use maybe a mean absolute percentage error as well, because it's mostly used for.
Yeah, but in training, mean absolute, I mean, this would be like a problem in the training because of the non-convexity of the loss function. So another thing that I'm curious, I mean, you validated everything pretty nicely. So have you done any cross-validation? Because you have different types of data sets. So while dividing the data to training and validation, was it like randomly divided or how? I mean, was it always fixed?
Yes, it was always fixed.
What I advise you would be like, do this kind of cross-validation stuff. That you switch amount, you move, you swap the training validation data sets and so on. And other thing, okay. On the 17th slide, so just before the next slide. So the results that you have presented here, are these like an one step ahead prediction or multi-step ahead prediction?
Those are one step ahead.
So how would the system perform for multi-step ahead prediction? So if I would just give you the data up to 2014, and if I would say you, can you predict the characteristic up to 2021? Nice to see these kinds of multi-step ahead predictions. Because at one step ahead prediction, basically it's quite difficult to assess the quality of the model in general. But it looks like we have also another question from the audience, Adi. So he asked, which algorithm you use for the graphic and how many validation? I think the size of the validation.
This is the size of the validation.
Yeah, I think it is. I mean, it's written how many validations, so I guess the size of the validation data set is.
It's, I mean, it's 30%, but you know.
Okay. So which algorithms have you used for the graphic?
For this one?
I have no idea. So Adil asked the question, so I'm
okay,
just reading.
Okay. Decision integration strategy that I mentioned.
Okay, so I think, okay. So are you fine, Adil, with the answers? I don't know. If not, just raise your hand and unmute yourself. Okay, looks like thanks. So
Thank you, Adil.
there are no further questions. This was, I think, the last presentation of the AI session number 2. So I would like to thank everyone again for joining this session and Hassan for doing the final presentation of this AI session. So if there are no comments or questions, then I think that's it for this session. So have a nice day. Ciao.
Thank you.